Okay, I received a few questions about homework 10, and I want to address what I think might be some of the sticky points that will help some of you to complete the homework assignment. So specifically on problem 2, there are two charges, and I'm not going to actually do all the calculations, but I'm going to show you how to set up the problem so that hopefully you're able to follow through. And you can also watch the Zoom videos of classes this past week where I discussed this, and also the week before, I think the Thursday before, I also did problems similar to this. Now this is not a dipole, these are two positive charges, this one and this one. And what I'm interested in this problem is eventually to determine the electric field at that point. And the way we determine it is by finding the electric field associated with this charge at that point and with this charge at that point, and then combining those two results to get the overall electric field. So this is similar to problems we've done earlier, but I think in some of the problems you've seen in other cases, the point of interest was below the charge. In this case, it happens to be above it, but we have the distances. So we have 10 centimeter distance here, and then 5 centimeters here, and here. So we do have the symmetry that you'll always have when we deal with two charges and a point of interest that's not on the same line as the charges. So the way I would do this is I would find the electric field at point X. I'm going to start with charge 1. I'm going to find the electric field at point X caused by charge 1, and it's going to be in that direction because it's going to be radially away from the charge. And so the line connecting the charge and the point, if you extend that line and put an arrow on it, that's going to be the direction of the electric field associated with that positive point charge at that point. All right, so I need to find the electric field at that point. And the way I would do it, of course, is I would use this equation for the electric field, K times Q over R squared, where R is this distance here. And you'd need to find that distance using Pythagorean theorem because you know the two sides of this right triangle. So you can find the third side using the sum of the squares. And that would be the length of that side squared. So, of course, R squared is equal to 5 squared plus 10 squared in centimeters. Then convert it to meters. Plug it in this equation. The Q is this Q right here. This would be Q1. And then K, of course, you know. So that would be this electric field here. And I would need to determine its X direction and its Y direction. On the angle, it's asking for an angle. It says what would be the angle. And so the angle for EA, I guess, is, I think I call this A and this one B, if I have the problem correct. Yeah. The angle of interest is that angle there. So you can use SOHCAHTOA. This angle here is going to be the same as this angle here. All right, and so this is how you find the strength of the electric field at that point, and then you want to find the X component and the Y component of that first one, and that's equal to E1 cosine of that angle, and E1Y is equal to E1 times the sine of that angle. And this is going to have the I hat, and this one's going to have the J hat. And the important thing to consider is it going to be a positive or a negative in front of the I hat and J hat? And for this case here, you see that the arrow is pointed in the positive direction for X and the positive direction for Y, so they're both going to be positive. Then for E2 or EB, I guess, is how it's worded in the problem. EB, it would be the same calculation, K times QB or Q2 over R squared. And that would be this arrow here, I'll draw it in blue. That represents the electric field caused by the charge on the right at the point X. So my goal here is I need to add the blue arrow and the red arrow together. I need to add those two. And you can probably see that they're symmetric, so they're going to be identical in size. The angles are the same, so this angle here is going to have to be the same as that angle there. That's one of the other questions that's asked in this problem. Now, this angle here, the problem's actually asking you to find that angle. So it's going to be equal to this, to 180 degrees minus this angle here. So for that second angle that you're going to find in the problem, that's how you would go about that. But you need to find the the x and the y components of this, and you do it in the same way that you did it for this one here, for this case here. The only difference being you have to determine which ones are positive and which ones are negative. And hopefully you see that this arrow here, the blue arrow, is pointed upward, so it's going to have a positive y component, or plus j hat, but it's also pointed to the left, so its x component is going to be negative, or negative I hat associated with that one. So the negative of the blue one and the positive of the red one are going to cancel for the x direction, but they're going to add in the y direction, so your result is just going to be something in the j hat direction. Hopefully this gives you enough of a clue to do all of problem 2. It certainly will give you a leg up if you were getting stuck on it. Then problem 3 is same situation. You still have these 2 plus charges here. Separated by 10 centimeters. And then you have the point of interest up here, 10 centimeters up. But at this point, now I'm asking you to find the potential at that point x. And the way that you're going to find that is you're going to find the potential at point x by finding the potential of charge A at point x plus the potential of charge B at point x. Now what's nice about this one, you did the harder one. Problem 2 has all these angles and I hat and j hat components, but potential doesn't have any angles. It's just a value. So in order to find this one, you need to find the potential associated with this charge at point x. So I'll write that out here. VAX is equal to, the equation for potential is K times QA divided by R. All right, so that's how I'm going to find the potential at point x. Now Q, this is a positive charge. There's no absolute values for this part of the problem. So that's 5 microcoulombs there. And that distance R, again, you're going to find that using Pythagorean's theorem. It's going to be the same distance you found in the previous problem, because this is 5 centimeters and that's 10 centimeters. So this is R, I guess R1 or RA. And that's how you're going to find that distance R. You're going to do the same thing for B, for charge B here. And the potential at point x caused by charge B is going to be K times QB divided by RB. All right, so you're going to find those two, you're going to add them together, and that's going to give you the potential at point x. And that's what problem 3 is looking for. Problem 4, I think, is relatively straightforward. The issues with problem 4 and 5 are just thinking about axes mostly. What does an axis mean? So I just want to point out how to deal with axes. Normally we think of the y-axis as up and the x-axis is to the right. But in 3 dimensions, we also actually have a z direction, which represents the vertical direction. And the way it's typically done is the z direction is that way. If you could draw it in 3D, you can imagine almost a cube here. This is one side of the cube, that's another side, and this is the other dimension. Okay, so that's x, y, and z. So in problem 4, for instance, it's asking for, it says that there's a line of charge that's infinitely long and lying on the z-axis. So that line of charge would be like this. And then it says, find the strength and direction of the electric field associated with this line of charge at a certain point. And I give a coordinate for the point. I say 0.5, 0, 0. And that refers to meters right here. And so what this means is this is the x-coordinate, that's the y-coordinate, and that's the z-coordinate. And so the x-coordinate of 0.5 is going to be right there, but the y of 0 is going to be at that same point, and the z is also 0. It's also going to be at that point. So we're really just looking at a point that's half a meter on down the x-axis. So it's only a half meter away from the line of charge, so that's your r. And I gave you an equation for the line of charge for the electric field associated with that, and that's what you'd apply in this case. And then I have you do something similar. I think I give you different points to find it at, and to determine both the direction and the strength of the charge, and the strength of the electric field caused by that. Now the strength of the electric field for a line is given by the okay, for the line of charge, the electric field strength associated with the line of charge is 2 times the linear charge density, that's coulombs or microcoulombs per meter, 2 lambda times k divided by r, or 2k lambda divided by r. The order doesn't matter on top, of course. And the direction of this is going to be, if it's a positive line of charge, in other words, if the charge density is a positive one, it's going to be away from the line. So that would have to be specified. So if the line lies on the z-axis and it's positive, and you're located here, the electric field is going to be pointed that way. Similarly, if you're there, electric field will be pointed that way. Okay, so this is the electric field associated with a line of charge, and it would be this strength with the absolute values around the lambda, with the direction given as I just described right here. All right, for the plane of charge, we had this expression that we came up with in class, and I gave it an error. There was a missing factor of 2. For a single plane, the electric field strength is going to be given by this expression right here, where it's sigma, which is the planar charge density in coulombs per square meter, divided by 2 epsilon 0. I gave it this equation without the 2 in it in the denominator. It needs the 2 for a single plane. All right, so if you have a single plane here, and in the homework, the plane is aligned with the xz direction. I'm sorry, the yz direction. So y is this way, x is this way, z is that way. So the plane of charge lies here. And then I ask you to find the electric field at different points. Any point here. And what's nice about the plane of charge is that if it's a positive plane of charge, or negative, but no matter, as long as it's a plane of charge, the electric field anywhere on one side of the plane is going to have this value. Notice there is no r in here. There's no function of distance in this equation. It's only given by the charge density and 2 epsilon 0. So anywhere to the right of this plane, it's going to have this value. Similarly, anywhere to the left of the plane, over here, it's going to have the same value as well. It's just going to be pointed in the opposite direction. So if this were a positive plane of charge, which I generally draw as red, to the right of the plane, it would be in the plus x direction, or I hat. To the left, it would be in the negative x direction, or negative I hat, the way the plane is oriented in this case. Next part of the problem, on problem 5, I say if you have 2 planes, so this is a side view of the planes, so you don't see that they're planes here. But if you have 2 planes, and the one on the right is negative and the one on the left is positive, remember the electric field lines go from positive charges out to negative charges. They're always going to negative charges, and they're always going away from positive charges, even if the positive charges lie in a plane. So for the positive plane, the electric field lines would look like this. Notice they're parallel, as they are for planes, because the electric field strength is the same value no matter where you are, here or here, it's always the same value. That means the electric field lines are going to be parallel. For the negative plane, and I'll draw these in blue, the electric field lines go towards the plane throughout all space. And I should have drawn that these green ones continue over here too. So if you look at the regions outside of the planes, out here and out here, the 2 cancel. In between, which is here, they reinforce. Since the planes have the same charge density, just that one's positive and one's negative, in between them, the electric field strength is going to be twice the electric field strength that it would be associated with either plane by itself, because the 2 effects reinforce each other. And this is where you get the equation sigma over epsilon 0 for the electric field strength in between the planes. And in this case, of course, it's directed to the right, because it's always directed to the negative plane from the positive plane. Okay, I hope you find this helpful.